I should also start my Zoom camera.
Yep.
Okay.
That way people can see you.
Okay.
Oh, something is coming there. What happened, Rick? Can you stop sharing screen for a second? Because otherwise you're just getting me.
Yeah.
So we've forced ourselves to make things so secure that you need OTPs and whatever else to log in. And once your computer crashes, it means it's 5 minutes before you can log in again. We've done that now, and there we are. Hello, online audience. Hello, everybody who's here. First Sunday of the month, time for Chai and Why. And I think we're in for a treat today with Radhika. But first, for anyone who's here for the first time or anybody watching us for the first time, Chai and Why happens on the 1st, 3rd, and if a month has a 5th Sunday, the 5th Sunday of every month. The first Sunday is here at Prithvi, 3rd Sunday at Ruparel College, 5th Sunday is on a mobile device near you because we're live from the lab in TIFR. A request, especially to the online audience, we cannot hear you. Please put in your questions in the chat or Q&A and we will take them up. If you're watching on YouTube, put it in the comments. I will be monitoring the YouTube comments, and if I find something interesting, I'll interrupt you and tell you if it's that important. If it's about black holes, I won't interrupt you.
Yes.
So yeah, folks, please come in and find yourself a place to sit. I would recommend everybody with a mobile phone to keep it on silent, please. We'd like to hear Radhika and not music from phones. What's coming up 2 weeks from now at Ruparel is
friction in action.
Yes, it's about friction. So 2 weeks from now at Ruparel, it's all about friction in action, how we see things with friction in everyday life. And after that, a month from now is September 3rd, Sunday. And I haven't found a speaker, which means it's me, because the show must go on. So I think I will talk about the wheel, just reinventing the wheel. We will reinvent the wheel somehow. So I'll do something. It's going to be on the wheel. I'm sure it's going to be. So that's what's happening. And now let's introduce the speaker for today, Radhika Gupta. She's a faculty member in the School of Mathematics at TIFR. And she actually started off being an engineer/physicist like someone else. So she is technically my junior from engineering physics in IIT Bombay, though separated by many years. And after doing her BTech in engineering physics from IIT Bombay, she went to the University of Utah, where she did a MS and PhD in mathematics, and then eventually found her way to TIFR, where she's in the School of Maths and works with stuff that I don't understand. But she also spends a lot of time getting the excitement of mathematics, which is not those solving, nobody buys 113 erasers and 25 pencils and finds out how much profit they've made. Those are like that's not math, right? The fun in maths is what she'll tell you about, right?
I'll try my best.
And apart from that, she's a brilliant artist. Her website has some amazing pictures of stuff from the local train and everything else. So over to you, and please ask questions, especially all you kids. If you don't understand something, please ask a question, okay? We'll try and take them. If it cannot wait till the end, do put up your hand and ask. If not, ask them at the end. So over to you.
Thank you so much, Arnab. Thank you to the. Oh yeah.
Yeah,
I can.
Just remember that it's going to be on YouTube forever. So you can always. If you insist on taking a photograph, sure, do that. Just tag at Prithvi Theatre, tag at Chai and Why, and we'll be more than happy. You can go back
no,
to sharing.
Yeah. I would like to start by thanking the TIFR outreach team for giving me this chance to speak here. I'm really excited to tell you all of you about a little bit about symmetries, but a lot about symmetries, a little bit about groups, and what kind of things I think about. So before I start, the goal of the talk is to get you started on trying to understand symmetries and groups. so that after this talk, you can go home. There's like a bunch of information on Google, Wikipedia. So this will give you a stepping stone to learning these things on your own. All right. So I'll start with two quotes that I really like. So this one is by von Neumann. If people don't believe math is simple, it is only because they don't realize how complicated life is. So in maths, we have like a bunch of rules. Sometimes you have to discover the rules. Sometimes you make those rules. But there's a lot of um, uh, random things don't happen in a way. There's a lot of structure there that is you can grasp or you can hope to grasp. Life can be very crazy. And the second quote is by Herman Weyl. So symmetry, whatever you think of symmetry as, is one idea by which humans through ages have tried to comprehend and create order, beauty, and perfection. So today we'll see how to detect some kind of symmetry. Okay, so let's begin our journey. Hopefully we will climb the mountain a little bit today. Okay, so this slide has a lot of pictures, and I would like you to tell me what kind of symmetries do you see, like whatever symmetry means to you. I haven't told you what I mean by symmetry, but whatever symmetry means to you, what different kinds of symmetries are you seeing on the slide? I would like people to respond. Yeah. So like the same pattern is repeated over and over. Right. Right. So that's called like fractal behavior or self-similarity, something like that. Somebody else. Right. There are rotations. So like the flower has some rotation. The snowflake, somebody was saying. There's also reflection. Taj Mahal there are two reflections, one in the water body and then one which is bilateral. Say that again?
Linear symmetry.
Linear, yeah. Yeah, you can call it linear symmetry or bilateral or mirror symmetry. You can use lots of different words.
Five-fold symmetry.
That starfish, right. So starfish has five. What does five-fold mean? You can like twist it 5 times. Translational symmetry. In this last picture?
Yeah, the last one, the honeycomb.
Yeah, and the honeycomb, right. They both have what I mean by translation means shifting. I can shift in some direction and I'll see the same thing.
I think that is a parallel from Alhambra.
Yes. Yes. Yeah, I'll say a few more words about this kind of symmetry later. Does anyone else see any?
Crystalline symmetry, that is something in the last two.
The snowflake?
Not the snowflake.
This one. The ball is actually don't know what name to give this. It's like a complicated shape, and really if somebody gives it to me in my hand, it will take me quite some time to figure out how do I rotate it, how do I do what to it so it stays the same. I don't have a name for it, but yeah, it will have some complicated set of symmetries. Coffee is again bilateral mirror, right? So great. So everyone has some intuition.
So I think there are fractal patterns in the snowflake and the
Yes. Yeah. So the leaf, somebody said fractal, like the self-repeating thing. Snowflakes in this picture we can't see, but yeah, snowflakes also have that kind of symmetry.
somehow are two mics on both your.
Should I switch off the Zoom mic?
Switch off the. I mean, just make sure Zoom is connected to your collar mic and not the iPad mic, because I'm hearing everything twice.
I see.
You need to select the microphone. Your device. I can hear them. I can hear them. Some mic is on.
It's connected to Bluetooth only, I think. It's good now? Okay. Okay. So let's see, what is symmetry?
On the net, people have said reflection, rotation, translation, inversion.
Awesome. I think that's pretty much the answers we got here. Awesome. So have people read Calvin and Hobbes?
Yep.
Some people, 2 people know what transmogrifier is. So it's this like box that Calvin goes into. He thinks he's turning some dials and then he'll come out as whatever he wants to. But symmetry is the opposite of that. So instead of like the transmogrifier here, I should write some kind of transformation. But the idea for symmetry is you step into this chamber, you adjust some dials, and they have to do something. You can't just like not adjust the dial, but then you should come out as it is. That's symmetry. Like things shouldn't change. So a symmetry of a space or an object is an operation or transformation of the space that does not change it. If you want to do something to the space, that it doesn't change the space. Of course, what does it mean to change the space? You have to define it in. If you want to do it formally, you have to define it for different things, but roughly. And I think of a symmetry as a map from the space to itself, or as a function from the space to itself. So if you've like, at least in school, we write f of x equals to blah, 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 right? So like x for me is the whole space, and then it just maps to the whole space, roughly. I'm thinking of it as a map. Okay, so I have 2 pictures here. What symmetries do you see in the first picture? No symmetry. And in the second picture, the mirror symmetry or bilateral or inversion or flip, like all the words which we were using. So that's correct. But since I'm thinking of symmetries as maps of my spaces, I want to introduce this symmetry called do nothing. I don't want to say no symmetry from now on. I want to say do nothing. I want to think of that also as a symmetry. So in the first case, like doing nothing is a symmetry. And in the second case, doing nothing and that flip. Those are the 2 symmetries that I can find.
Talking in terms of operations.
Yes, I'm thinking of it as an action I'm doing. Like I'm taking this thing and I'm doing something to it. Yeah. Yeah. Oh, no, okay. So doing nothing with the function would be the identity function. Like every point on my space will go to the same point in the space. Yes. Okay, so let's do some examples. So I have a triangle or a samosa. I'm thinking my samosa doesn't have any potatoes in it today. It's flat. And so I want you to tell me or think how many symmetries will a triangle have? I'm not allowed to flip the triangle. I'm only allowed to just move it. 3. 4. Yeah. Yeah, you want to count nothing, do nothing as well. Okay. Maybe think a little more, and including doing nothing, is it 3 or 4? 3. Okay. So do you want to say how 3? A reflection, right now I'm saying let's not think of reflection. We'll think about reflection in 2 slides. Rotation. Huh? Right. So okay, let's do this slowly. So I've put some numbers on my triangle 0, 1, 2 just to keep track of, so that I can keep track of the rotation. So let's say I rotate. Let's say I rotate. Let's call this R clockwise by 120 degrees. So if I do that, I get 0, 1, 2, and I can rotate again by 120 degrees. So R is my notation for rotating clockwise by 120. I get 0, 1, 2. And if I apply R again, if I rotate again, then I get the same thing back. So it's actually only 3.
So if I take the spin in the other direction, then do you fix?
Thank you for asking that question. What happens if I spin the other direction? What if I was doing clockwise. Right, it will just be the, like if I do counterclockwise, that's called, can I call that, I'm going to use this notation, R inverse, because I'm thinking of these as functions and I'm doing the opposite function. So the counterclockwise will give me this. This will be one more counterclockwise. So we had, so I've written it here. So if R is my rotation by clockwise by 120 degrees, I have the do nothing, rotate once, and then this is my notation for like composing functions. Since I'm thinking of these as functions, this is rotating twice. And why did I stop here? Because if I rotate thrice, if I do R cube, I end up at do nothing again. Yes. Yeah, if you know mod 3, then this is just that. This is a geometric way of thinking of mod 3. So that's it. These are the symmetries. Because if I do R3, I end up with do nothing again. So, okay, what are some, I want to highlight something. So there is the identity, which is do nothing. Composition, if I take two symmetries of the triangle, if I compose them, what does composing mean? Do one symmetry and then do the other symmetry. It will still be a symmetry. And what does cancel mean here? Like for every symmetry, I can find a different symmetry which will undo it. Like in our example, it was this, like the rotation clockwise has a rotation anti-clockwise. And okay, here's a question. In this set of symmetries that I wrote down, I only wrote the clockwise rotation. I wrote R as 1 clockwise, R square as 2 clockwise. I didn't write the anti-clockwise. Exactly. So in this picture, can you like the anti-clockwise? This is same as doing R twice, doing the clockwise twice. That's why I didn't write the anti-clockwise separately.
In essence, what you're saying is there are 3 states, 3 symmetrical states. There may be 100 ways to get to those.
Right. I'm actually saying there are only 3 ways to get those also. Okay. Because I'm thinking of these symmetries as like the action I'm doing on that. Yeah. In more complicated situations, you might get to the same state by different things. But here, there's a one-to-one correspondence between how I'm getting to that state and what that state is. Awesome. So I'm being very careful about not repeating my symmetry because I want to have a good set which describes the symmetry. And it has these 3 properties. There is the identity, the do nothing, there's composition, and there is the thing that cancels every symmetry.
Are these meters all sorts of symmetries? Would all symmetries have identity, composition, and cancellation?
We'll see that. Okay, sorry. So the question was, do all symmetries have these properties of having identity, composition, and cancel behavior? Yeah, we'll see that. Okay, and then I've used this notation C3 here for this group. And that's basically called the cyclic group of order 3. Doesn't matter what these words, like, we understand what the group is. This is just like useful notation. There was a question here.
So when you put your overcast flat and you're saying if you put it vertical and do some other transformation in another dimension down there, does it come down to boil down the same thing or is there another way of it?
So when you are, yeah, so we'll come to, so the question is like if I if my samosa is flat versus if I like make it vertical in 3 space, and then I want to know its symmetry is in 3 space, not like in 2 space, then do I get something else? The answer is yes. And because in 3 space now I can think of like also reflecting it. So we look at that group, that set. Okay, so let's do some quick exercises. So if I have a square, so I'm thinking of waffle here, again, a flat waffle. Again, I'm not allowed to flip it. How many symmetries will a square have? 4. 2? Which 2 ones are you thinking? So R is what for you? R is rotating by 90 degrees? 90 degrees. And then I can do 180. And then I can do 270.
Here will be one is rotation, because once you rotate 90 degrees, it remains same. The other will be translation.
So I'm only thinking of the square by itself. So there's no translation here.
Only square.
Just the square by itself. Huh. Sorry, I see it. My picture is, yeah, I should draw. I'm just thinking of this one big square. Yeah. How? My waffle has smaller squares in it, but I'm ignoring that. Good catch.
You are assuming that the 4 corners are different?
Yes.
Yes.
Yeah.
That will give you 4.
So I'll have 4. It will be 1. Then rotate R, which will be rotation, let's say clockwise by 90 degrees. Then 180 degrees, 270 degrees, and then I'll end up with, this will just be 1. If I do 360-degree rotation, that's just doing nothing. So it's, yeah, right. Basically 4. It's a set of 4 elements. Starfish, 5. So in short, we say it has 5-fold symmetry, 5-fold rotational symmetry. Yeah, I'm only looking at.
Rotational C.
Yes. Cyclic. Yeah, that's the C for cyclic.
It would be same for a pentagon.
Yes. So here is my pentagon. Exactly. Yeah. Oops. Okay. So now let's do triangle with flips. Like you want to put the samosa in 3D. So let's allow flips to it. So I have my 3 rotations, or 2 rotations, 3, however I want to think. Now, if I flip it, how many more should I add? So I'm getting all the answers from 1, 2, 3, 4, 6. So you're telling me the total number of symmetry. Yes. Yes. Total 6. Yes. So how many flips? Everyone's thinking flip. How many flips should I add? 3 flips. 3 flips, which are exactly these. Flip, like again, I've numbered my vertices. So the flip is about the first black line or the second black line or the third black line. And there are 3 different flips. Right? So I have 1, R square. I'm calling these flips S0, S1, S2. And then the dot, dot, dot is question, is there more? What if I compose these symmetries? Like if I do rotation first, then I flip, do I get something new or do I just get one of these ones that I've already determined? Everyone's very sure. Good. Let's check. Let's check some things. So I do rotation first, and R here is clockwise rotation. So clockwise rotation 0, 1, 2, and by S0 was this flip. I get 2, 0, 1. Does this look like, can I go here directly?
Yes. We can go to the only by the flipping. Only by flipping we can go there.
Only by flipping I can go there. If I flip this thing, that's S1.
All 6 will suffice for everything.
Yes.
Supposing any new
It's already in the set. Yes. So here what happened was I did R first, then I did S0, and I end up getting S1. So when I'm writing R, what does this mean? I'm thinking of function notation, like I do R first, then I do S0. Okay, so then I'm getting S1. But let's do S0 first. What if I do the flip first and then the rotation? Then what do I get? Do I get the same S1 or I'll get S2? Yes. So let's do it slowly. The flip gives me 0, 0, 1, 2, and then the rotation gives me 0, 2, 1. And this is S2. So one thing to note here is like the order in which I do these symmetries does not match up. The fancy word is it's not commutative, but like basically they are different things. Okay, one more exercise. What if I do R square and then S? S is what? S0. What do I get at the end? 1, 0, 2. Okay. 0, 2. Okay, let's check. So if I'm rotating it twice, so it's 0, 2, 1, and then flipping. Did I do that correctly? No. I did that wrong. 0, 1, 2. Now I flip. Yes. 1, 2, 0. S0, okay, thank you for asking that question. Yeah. S0 means that vertical line. No, it's just a vertical line. Yeah, the numbers are for me to keep track of things, but it's the vertical line. So S0 is this, S1 is this, and S2 is this, in whichever position I am. Question? I'm not cutting it. Imagine, yeah, I'm not cutting it. Imagine there is a mirror here. And so then I see the same image if I reflect in that mirror. Or I can imagine like I have, if in 3D I want to imagine, I have my triangle and I just like flipped it. Yeah, like about that. Or like imagine like if there's a line going through me and if you like flip me, if I was just like not 3-dimensional but 2-dimensional, I will look the same, right? If you just flip me. So that's what I'm doing with the triangle. I'm just flipping it. Yeah, I'm not cutting it. Yes. The question is, what if the triangle is standing on the like this? It's the same. So I'm just keeping track of, because I the symmetries won't change.
You define your operations from the initial how you kept it based on that.
Right.
So then you change your operations accordingly.
Right. The way I'm defining symmetry is
Your operation will not change.
I'm starting with one particular way I place the triangle, and I want to see what all operations I can do on it such that I get the same thing back. So you could like, I could have instead of drawing my triangles like this, all my triangles could be the way you want them. But then I would have to make all of them like that. No, I'm doing equilateral triangle. Yeah, because if I don't give you, right, because if I give a non-equilateral triangle, if you rotate it, you'll not get the same thing. Yeah, this is all equilateral triangles, regular polygons. Yeah. Okay, let's do one last exercise. Let's just do one of these. If I do R, then I do S, then I do R, then I do S. So rotate, reflect, rotate, reflect. What do I, did I end up doing nothing or did I do something? Okay. Let's see what other people. So what is S? Sorry, I think did I say what S is? Let me. The first one is not? Okay. Somebody else disagree?
What's the number?
Okay, so
Should be R square, yeah.
should be R square? Okay, what was SR? So let's go back. If I do S first and then do R first, then R, I get S2, right? What was S2? It was a flip. Yes. So actually it's 1. And maybe you can, so here is an exercise. This is actually a hard problem in math. Like you have come up with some symmetries. And what if you just like keep doing them in a random fashion? How do you know you end up with doing nothing? For some groups, you can actually like write an algorithm to solve that question. But sometimes you just, so yeah, sometimes it can. Right. But if I give you like if I say like rotate, reflect, rotate, reflect, rotate, reflect like 10,000 times. So manually it's not. So for some groups, you can write an algorithm. So like people use this in cryptography. Like if it's easy to write an algorithm, then that's a bad group. Right. This group is easy enough that you can actually like just do it by hand. But in general, you might not be able to.
Mod 2 for this group, for it to be unitary, that you shoot as R as R.
Yeah, for this one, yeah. But the groups where you can't tell this easily, there are groups where somebody has proved that you cannot prove this. Like you cannot find an algorithm to find whether it's trivial or not. Those groups are the good groups for cryptography. Because then somebody can't easily intercept your. This is vague, but I'm just trying to tell you that this is a hard thing to check. Okay. I've drawn a picture. This picture is supposed to capture everything we did so far. So this picture is, people try to understand symmetries by drawing these pictures. So I started with this configuration and I was trying to see what moves can I do to it such that it stays the same configuration. So I can do rotation, rotation, rotation. I can do these flips. So for S for me is the vertical flip. I can do flip here, I can do flip, flip, and then I can rotate. And that's it. From this diagram, I can easily read, if I do now R, S, R, S inverse, blah, 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 I can like read from this. So here, it will actually be not hard to figure out when you get something to just do nothing. Okay, so let's just write this a little formally. So R is my rotation by 120 degrees clockwise. S is the reflection about the vertical line, and the set of symmetries. So I have.
Why is it called D3 here?
Right. It's not C3 because it's called dihedral group. C was just cyclic, and this is dihedral. So dihedral actually means, like, you might have seen dihedral angles maybe in like geometry in school, which is like angle between two planes. You have two planes in 3D. There is a way of thinking, because I'm allowing these reflections in 3D, there is a way of thinking of this as like two faces. That's why dihedral. And so this was my S0, this was S1, and this was S2. And again, I have identity, I can compose symmetries, and I have the cancellation effect. Like for rotation, we saw what the cancellation thing is. For flip, what's the cancel? How will I cancel the flip? Just do it again. Yeah. So flip is its own cancellation thing, inverse. Okay. So just saying Cn is the cyclic group, just the rotation. Dn is the dihedral group, which is rotations and reflections. And we define these only for n at least 3. Defining it for like 1 gone, 2 gone, that gets a little fuzzy. So we don't go there. At least in this talk, we are not going there. Okay. Yes.
So I had a question for the triangle, and that may not be related to what you're talking about, but I saw this on Instagram, like if there's a triangle and you do a vertex and a random point in the triangle, and you plot the points midway between the distances, and you keep repeating that process, the pattern will start forming inside the triangle.
Mm-hmm.
So is that related to this thing, like repeating, rotate, and that?
It's not related to this, but there would be other kinds of symmetries. Like the pattern which you would get, it would have some other kind of symmetry there.
Does a like point start forming and you start forming triangles inside the triangle?
Right.
And inside the triangle.
So somehow like the angles at which you're drawing the line, and like those will have some kind of pattern, but not in the, so I'm talking about spatial symmetries, just like when I look at it, how do things change with symmetries? Okay. Maybe before symmetries, how many spokes does the Ashok Chakra have? Okay, everyone knows that. Good. So how many rotational symmetries? 24. Somebody said something else. 1 plus 23. Yeah. And how many reflection symmetries? 24. Infinite.
If I take every angle or even the fraction of angles, it will give me the same reflection. Why am I taking my mirror on every angle? You want to be able to get it has to come back to itself.
So let's number these spokes. 1, 2, 3, 4. $12. Somebody said 12. I like that answer.
You could also do axis, that plane which is between.
Yes. So I can choose either the line passing through the spokes or the one which is between two spokes. But then do I need 24 green lines or do I just need 12 green lines? Just 12 green lines, right? Just 12. And then 12 yellow ones. So that's 24. In a triangle, it was, yeah. In a triangle, it was different. I had to do it like through every vertex. But it's because this is even numbered. In a hexagon, it will be. In a hexagon, I'll have to do both these and more.
So how do you kind of like find these symmetries? Use the trial and error by seeing like how many you can find pretty much?
Like right now, that's what we are doing. Oh, the question is how do we find these symmetries? Is it just trial and error, or is there like a better way of finding these?
So between 1 and 2, you've drawn one line. Why just one? How do you
So I've drawn the one which is like equal angle. If I don't do equal angle and if I reflect about it, then I won't get the same chakra back.
for example, that dot, you take some, take an angle of 5
Let's say the total angle.
divided by how many?
Right. Let's say the whole thing is, let's just do, let the whole thing is 10,
Right.
and you want to do 3 and 5. Oh, sorry, 3 and 7.
Okay. 3 to 4 and 6.
Yeah. So let's say the whole thing is 10,
Yeah.
and I do 6 here and 4 here. Now, if I reflect like this green thing, I'll have to make a 6-degree angle here for it to reflect. Yes. Huh. And that question was good. Like, do we do this just by trial and error, or is there a system to doing these?
Can we consider maybe one specific section, and then all the other ones are composite with rotation and reflection, you get 24. And I'm not about the last one for the between.
That's a good thought. Like you were saying, just take one of these greens and then just use a rotation to move it around. Yeah, that's what I did for the triangle also, right? I mean, initially I said S0, S1, S2, but then I just, like when I finally wrote it down, I wrote it as S, then RS, and then R square.
When you ask what are the possible actions? The possible actions is the set, right?
Yes.
All the unique actions. So for that, you only include one set.
So these questions are like, is someone asking you to list all the symmetries, or is someone asking you to list the 2 symmetries which will give you every other symmetry? Like if I just play with those 2 symmetries, will I get like here just one rotation and 2 of these reflections? They are enough to give me all the symmetries. So these are also questions that people study. Like even let's say I know the whole set of symmetries, figuring out, is 3 enough? Like, can I understand this by just using 3 or just 5? Those are also hard questions to figure out about groups. Okay, I already used the word group.
Why would you do of the reflection?
One is the one going through the spokes, and the one is between the spokes. Yeah. 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 So I'm already using the word group, even though I haven't defined it. What? Yes. So this is now like, this picture is like abstract, showing that now I'm going to like find some, like, to take some structure out of these random examples that I'm doing. Yes. Mm-hmm. Can you write off? Right. So if I do, so like I've written here dn, right? If I have an n-sided polygon, I can write a formula for all the symmetries. That's what I was trying to say. So I will have R, I will have S1 or S2, depending on whether it's an odd, if n is odd or even. And then I will have, I guess I will have R squared all the way to R n minus 1. So for triangles, we did R squared. We stopped at 2, not at 3. And then I will do RS, R square S. So I can just using R and S, I can write all the symmetries. There's a nice formula way to write these things. I wrote S1, S2 because like for the Ashok Chakra, we had 2, right? We had 2. That's all. That's why I wrote S2.
That's why you call it group, because we are making a shift like this.
Yeah.
Right now it's a set.
Okay, I think let's go ahead, because otherwise the tie will get folded.
Wait, how much time do I have?
Where is a good place to take a break?
Okay.
Around 12-ish, 12:15, you should definitely take a break, otherwise tie will get very cold.
Okay. So
Come back to condition, no problem.
Okay, let's formalize what we've been doing so far, and then we'll take a break. Okay. So now I want to define this thing called a group. Okay. So a group is a set of symmetries. with an operation. Think the composition of symmetries. So think of the whatever we were doing for the triangle, such that, okay, there's a bunch of text here, but don't worry too much about it. We've already seen these things, such that there is an identity element in that set. Identity is, if I compose my any other symmetry by identity, identity does nothing. So that's what I mean by this here. Like I is my identity. If I compose any other symmetry by identity, it leaves it as it is. The composition, any two elements in the set, if I compose them, then I get something in the set. If I take any two symmetries, compose them, I get another symmetry. And for every symmetry, there is a symmetry that cancels it and gives me do nothing. And the last one, I wrote it there just for completeness, but let's not worry about the last bullet point. So that's a group. Nothing fancy. It's just a set with some operation and with these three properties. You need the identity, you need the composition, and then you need the inverse. So what we were doing so far, like the rotations of a n-sided polygon, that's a group. The dihedral symmetries, that's a group. Let's do some more easy examples of groups. We all know how to count. So let's see, let's do it with numbers. So I have the set of numbers 0, 1, 2, 3, 4, 5, and so on, like all the numbers. And my operation, so that's my set. And my operation is addition. Okay, let's give half a minute to, or maybe half a second for others to think. Is this a group? So think, is there identity? Is there composition? If I add two numbers, do I get a number? There's no inverse, right? The thing that fails here is, so there's identity. 0 is the identity. If I do 5 plus 0, I get 5 back. But if I take 5, 5 plus what should give me 0? Here there's nothing. We know it should be minus 5, but minus 5 is not here.
That's not natural number.
Right. So this is not a group under addition. But if I include negative integers as well, then it is a group. And these are called integers. And Z is the symbol for that.
Just a question, would there always be a single operator for the definition of a particular group?
That's the next slide. On integers, I can also multiply two numbers, right? I don't only have to add them. So that's your question, right? Like I can do other operations. So I have these numbers, negative numbers, positive numbers.
But for multiplication, I can always use positive as a multiplication, as we do in computers. Multiplication in computers done by adding things.
Right.
So I can do the same thing.
But is this a group?
In the positive. No, that's for natural, but for integer it can be done.
Multiplication can be defined that way. Yes.
So there is no need of putting multiplication exclusively separate. If I use only positive.
There is. Like it's a different operation, right?
So, but the
like
same operation can be done by using positive also.
But if I like here, if I multiply a number by 1, I get the number back. But if I have 4, what should I multiply it by to get 1 back? Can't do, right? I don't have fractions here.
If you only consider one operation, then that operation has to be known inverse for this to be a group. Yeah, in that definition, when we define a point about the inverse. So there, let's say your example, plus all the operation. Is it already considered that minus will be also there somewhere, or does the operation need to be inverse?
No. Okay, thank you. That's a good question. So here, when I'm asking 5 plus what should give me 0, and that what is minus 5. So I'm instead of saying 5 minus 5, I'm thinking 5 plus minus 5 plus minus 5.
So mine is a follow-up question. Can we define a group with multiple operations? For example, if we define a set of natural numbers with both addition and subtraction operations, then is the definition correct?
So addition and subtraction are not two different things, I would say. Like if I have this set, because of what I read.
Right. Since you are here, you have special privileges of asking as many questions as you want after chai, because after chai you will shut down the online. So just hold on, let her finish most of it, and then you can ask all these questions.
I was just going to do this last example, and then we can take a break.
But you won't be online after the break. So if there's anything you want to really get convinced, tell the online people, you might as well give them a glimpse of everything.
Okay. Okay.
You get very bored of the go for
chai. Okay, then I'll do that. So
but
try.
Let's just hold on unless it's super important and you can't understand. Let her finish a bit.
I guess I'm almost done with like the actual examples, and then I'll give you some like overview of things. Just to finish this is not a group because 2 times what should give me 1. In my head, this should be 1/2, but I don't have 1/2 in my set. Okay. Let's see. So okay, so we can do more examples after we come back from chai, but let's take a step back, and I just want to like say a few things about group theory. So symmetry groups, as you like, I think we've already appreciated that symmetry groups are hard to describe. Like you don't know what more is there, what happens when I compose things. So it's a very hard thing to do. And then you might wonder, like, okay, maybe given a particular thing, I can describe all its symmetries. Given another thing, I can describe all its symmetries. Are they the same thing or not? Like maybe these are complicated objects that it's not obvious to me just by looking, but maybe the 2 sets I got, they are somehow the same. How do I tell that? And then how many different groups are there? How many different sets of symmetries are there? These are all questions. These are all hard questions. But for something called finite groups, what's a finite group? If there's only finitely many elements in that set. So the examples we did were finite groups. We didn't get to example of an infinite group yet. But this is like quite an amazing result. And it's not just one person who wrote this paper. This is like tens and thousands of pages, like hundreds of authors. It took like 10 years of work, and people are still working on it, trying to improve those proofs to get a better classification. What do I mean by classification? Some way of saying it's this group, it's this group. So some examples I've written is like cyclic group. That's a family. It depends on n, cyclic group, dihedral group. There's something called permutation group. E8 is some special group, which will show up again. But it's quite an amazing thing. It's a huge collaborative effort to classify all these finite groups. But these are finite, and I've written the word simple so that I don't say anything false here. There are also these infinite groups. There are some groups which have infinitely many symmetries in them. And then you might wonder, can I classify them? Are they countably many, uncountably many? Like, can I put some restrictions and classify them? These are, again, very hard questions. And there are like lots of unknowns. Sometimes we can even find monsters, and like there's actually a thing called monster group. It's a group which has like 10 to the power 53 elements. It's like there's a separate reason to call it monster, but to me that's also like pretty monstrous. Finite plus 10 to the power 53. Yes. Let's see. So how did group theory start? Like very quickly, it started because people wanted to solve polynomial equations. Like we learn in school how to solve a linear equation, how to solve a quadratic equation, right? Everyone knows this formula: minus b plus square root of b square minus 4ac over 2a. I know in the US, kids are taught to like sing this formula. They learn it by singing it. It's very weird to me when I first learned it. There is a certain symmetry here. It just differs by this plus minus. There's a certain symmetry between these roots. Then you might ask, is there a formula for a cubic equation? Is there a formula for a degree 4 equation? Cubics we learn, at least I learned some hit and trial method in school, but I never learned a formula. And for quartic also, I never learned a formula, but apparently there are formulas for these equations. These are exact, yeah, for exact solutions, there are formulas for cubic and. Yes, exactly. So there is no formula for degree 5 and above. And Everest Galois is a person who showed that. I mean, he studied so like the symmetry in the roots, which I showed just for quadratic. He studied that and he was able to say that you cannot find a formula for polynomials at degree 5 and above. And this was basically the birth of group theory. You'll notice he died very young. He died when he was 21. And I urge you to go to Wikipedia and like read about him. He did all this when he was like 18, 19. And then he died. He died in a duel, like one-on-one. Yeah. So you should read why was he doing that duel, so on. But he basically, he's the father, he's considered the father of group theory. So he didn't formulate things quite the way we think of them now. Okay, then I want to say, groups show up everywhere. Like I'm doing some examples in mathematics. There's like physics, chemistry, chemistry, you have molecules, crystals. You see them everywhere. Even in music, like people study music theory and they use groups there. We were already doing this, like trying to understand some geometry by symmetries. This goes much deeper. There are geometries which are different than like the geometry we perceive. So I study something called hyperbolic geometry. And even there, to understand it, I have to understand its symmetry. I have to really understand some groups which act on this geometry and how this geometry is invariant under those group actions. So like groups really show up a lot. The last thing I want to say is I want to tell you about this recent amazing result that was proved for sphere packing problem. So the problem is in 2 dimensions, you want to pack as many oranges in a square box. You want to leave as little space as possible. Okay, finding an arrangement is maybe not that hard. It's pretty intuitive, like I've shown it here. But proving that's the optimal solution, that can be pretty hard. Like in 3 dimensions, also like you would see with the vegetable vendors, they have a particular way of stacking things. And people like Kepler conjectured in 1611 that that would be the optimal thing. But it was only proved in 98 and 2014 that that is the optimal packing. And Thomas Hale's proof was really long. People, 99% believed it in 1998, but then it took him another 10, 15 years to do a computer checkable proof. Then the mathematical community was like, okay, now we definitely believe you. So the recent thing is Marina Vyazovska at EPFL Switzerland, she proved the sphere packing problem in dimension 8 and 24. So in packing of spheres, and she proved in 23 pages that that's the most optimal packing. And then 1 week later, with 2 other mathematicians, she proved it in dimension 24 also. And she got the Fields Medal in 2022. She's the second female mathematician to get the Fields Medal. Fields Medal is the Nobel Prize of Mathematics, but you get it only if you're less than 40 years of age. So she's fairly young, when she proved this amazing thing. And if you're wondering why dimension 8 and 24, that's maybe you can look that up. 8 and 24 are somehow very special. And I think for now I'll end here, and then we can come back and chat more. Thank you so much.
Okay, so online audience, if you have some quick questions which you want to put in online, please put it in the chat. We'll take it right now, and then we'll continue. Meanwhile, while we wait for the online audience question, if anybody has a question, please ask. Give me some time to check it out. Yeah. So, any questions? What happened? Yeah.
We killed the
equation to find x in the quadratic function x squared. Is this a rearrangement of the x squared with the x plus c, right, for x?
What do you mean it's the rearrange? Can you ask your question again?
Yeah, over here, we are making x a subject.
X is the variable that I'm trying to find. Yeah.
But it's using the same function as x squared plus b. So what you ask for cubic equation, can we use the same for cubic equation? To get a formula to divide x.
That's the whole point. Yes, for cubic you can. we never learn it in school. In school, I only learned the hit and try, like look at D, look at the factors of D and see if one of them works.
Possible to do it for more than 3, like more than 2.
For 3, it's possible. For 4, it's possible. For 5, 7 above, it's not. There's a proof that you cannot find the formula for 5, 7 above. Yeah, that was the awesome thing about how group theory started.
And the group theory which is used in particle physics or physics area, is it the extension of the same thing or it's a totally different way of understanding?
It's just different groups show up there. The definition of the group is the same. It's just that a different, so like in physics, we live in R3, like in the space, and the symmetries here are translation. Like if I take a box, move it, it doesn't change the box. If I rotate it, it doesn't change the box. So we have translation, rotation, all those symmetries in this space. Like space-time is something in physics people study, right? Space-time, like in special relativity, it's not just space, but you add a parameter of time, like becomes a 4-dimensional space. The geometry is different there. So the symmetries there are different. They still satisfy these same rules of there is a symmetry which says do nothing. If I compose two symmetries, I get the same symmetry of the space. And for a symmetry, there's something that cancels it. So all that stays the same. But what is that symmetry? That changes.
Like symmetry's definitions is also changing because of that.
Right.
So a question from Anya online. Why is this word symmetry used? Where did the name of the word come from? And the origin of the word symmetry? Is there a reason it's called symmetry?
I don't know the etymology of the word. I should look that up.
Okay, good question.
Thank you for the question.
Yeah. Yeah.
I had a question. So I have not had interest in mathematics till now, not at all in fact, but I've got interested in symmetry because of my interest in art, Escher and Islamic geometry. Can you suggest a book for people who don't understand mathematics to understand more about symmetry?
So there's one book called Visual, you can write it here. It's called Visual Group Theory by Nathan Carter.
So Marcus, I cannot pronounce the name, is also written a book on symmetry. Majority of it, the people who are not mathematics students can understand.
Sorry, that's a popular science book, right? The question was, is there a good reference for understanding group theory for someone who does not have a math background? Yeah, I can write the name. I don't know the name of that book, but I think the author is Marcus. There is also a YouTube channel, 3 Blue, 1 Brown. Okay, everyone has 3 Blue, 1 Brown. He has really, I saw the talks on group theory, but I think in general, all their math talks are amazing. So if you want to, yeah, I would say start with 3 Blue, 1 Brown.
Also, there is a course on brilliant called Beautiful Geometry.
Okay. Okay. Okay, I'll write that here. I haven't seen that. Okay.
Okay. Okay, I do not see any more questions. So let's, for the online audience only, let us thank Radhika for taking us through this rather complex world of group theory. All of us here, please help yourself some chai outside and we can start the discussion and come back and discuss more. Okay, so let's do that. Thanks again. And we're going to stop the online thing here. Please continue to send your questions. If you have questions, you can email them to outreach, outreach@tifr.res.in, and we will send them to the speaker. Thank you very much, and keep watching Chai and One.